Somewhere in the universe, dead stars collapse into objects so dense that a teaspoon of them outweighs a mountain. These are neutron stars, the most extreme creations nature has ever made. Today we'll explore what makes them so powerful, so strange, and so unlike anything else in the cosmos. If you enjoy this journey, please like, subscribe and share, and tell us in the comments what surprises you most about these extreme stars. Thank you for watching. Now let's begin. The Milky Way is shaped roughly like a disk with a central bulge wrapped with several spiral arms made of stars and interstellar material. The Sun resides in one of the more modest arms, often called the Orion Spur, at a distance of tens of thousands of light-years from the galactic center. In the plane of the disk, cold clouds of gas and dust gather into structures that look in astronomical images like dark lanes against the background of starlight. Inside these cold, dense regions, gravity can slowly pull matter together into clumps that will form new stars. The spiral arms are not solid structures. Instead, they are regions where the density of material is a little higher and where star formation is more active. Massive stars appear most often in these spiral arms, especially in the dense knots and clusters where many stars form at roughly the same time. A massive star forms when a collapsing clump of gas gathers far more material than a typical star like the Sun. As the clump contracts, it heats up, and at the center a protostar appears surrounded by an envelope of gas that continues to fall inward. Over time, the central object gains mass until nuclear fusion begins in its core. For a massive star, this birth process tends to occur in a clustered environment, where dozens or hundreds of new stars share the same natal cloud. Young massive stars soon become visible because they are very luminous and very hot. They emit much of their light at shorter wavelengths, making them appear blue or blue-white in color to the human eye. These stars can be tens of times more massive than the Sun, and they radiate energy at a rate far higher than less massive stars. Massive stars are not scattered evenly across the Milky Way. They are concentrated in star-forming regions that trace the spiral arms, marking out the places where cold gas has been compressed and where gravity has overcome internal pressure. Astronomers identify these regions in many ways. Some are bright nebulae where the intense ultraviolet light from young hot stars ionizes surrounding hydrogen gas, causing it to glow. Others are dense clusters of hot blue stars that stand out against older, redder populations around them. Radio and infrared observations reveal cold molecular clouds rich in hydrogen molecules and dust, where stars are in the earlier stages of formation and have not yet cleared away their birth material. In all these settings, massive stars form live and eventually and rarely moving far from the regions where they were born before their short lifetimes conclude. The environment around massive stars is shaped by their energy output. Their light exerts pressure on nearby gas and dust, pushing it away and carving cavities in their natal clouds. Their stellar winds, which are streams of charged particles flowing outward from their surfaces, add further momentum to the surrounding medium. Over time, a young star cluster may clear a bubble in the interstellar gas with massive stars at its center, and swept-up material forming a shell around it. This process can both limit further star formation in some directions and trigger it in others, as compressed gas at the edges of bubbles becomes unstable and begins to collapse. Thus, massive stars help regulate the birth of other stars, even while their own lives proceed on relatively short time scales measured in only a few million years. Observers studying the Milky Way from within must reconstruct its structure from many lines of evidence, because dust in the galactic plane blocks visible light over long distances. Radio waves and infrared light penetrate the dust more easily, allowing astronomers to map spiral arms and star-forming regions that lie far from the Sun. Surveys in these wavelengths show concentrations of cold molecular gas, along with bright regions where young, massive stars already shine. They also reveal associations of massive stars, which are loose groups that share a common origin and move together through space. By tracing these structures, scientists infer where in the galaxy the most massive stars are found and how they are distributed along the arms. Within individual star-forming complexes, massive stars are often located in clusters. Some clusters are dense and compact, with many stars packed into a relatively small region. Others are more extended, with stars spread over wider areas while still sharing a common origin and motion. In many clusters, the most massive stars tend to be found closer to the center than lower mass stars, a pattern that may arise from the way stars form and from later gravitational interactions. Over tens of millions of years, some clusters remain gravitationally bound, while others gradually disperse as internal motions, and the tidal field of the galaxy pull members apart. As clusters evolve and dissolve, lower mass stars drift into the general stellar population of the spiral arms, while the most massive stars often end their lives while still close to their birthplaces. Because massive stars burn their fuel quickly, they serve as markers of recent star formation. A region filled with hot blue stars must have formed them in the relatively recent past, since such stars do not remain on the main sequence for long periods. Regions dominated by cooler, redder stars either have not formed stars recently, or formed mainly low-mass stars whose lifetimes are very long. By comparing stellar populations in different parts of the Milky Way, astronomers infer where and when the galaxy has been actively forming stars. In these reconstructions, massive stars stand out as signposts of recent activity, highlighting the spiral arms and dense clouds that provide the wider setting in which massive stars live out their short lives and shape their surroundings. Inside the Milky Way, the birthplaces of massive stars lie hidden inside cold, dark clouds of gas and dust that drift along the spiral arms. These molecular clouds, made largely of hydrogen molecules mixed with helium and heavier elements, keep their temperatures only a few tens of degrees above absolute zero, so the motions of the gas remain gentle and slow. Within them, gravity, turbulence, and magnetic fields combine to create denser pockets of material. In some locations, filaments of gas converge, raising the density where strands meet. When the inward pull of gravity in one of these dense regions exceeds the internal pressure that resists compression, collapse begins. The gas can no longer support its own weight, and it starts to fall inward toward the center of the clump. For a future massive star, this collapsing region holds far more mass than a region that will make a star like the Sun, and it sits in an environment where a rich supply of gas can continue to flow in from the surrounding cloud. As the clump contracts, any small initial rotation becomes stronger, because angular momentum is conserved. The material flattens into a rotating structure with a central condensation and a broader envelope, often accompanied by a disk of gas and dust that orbits around the forming star. At the center, a protostar appears. It is not yet in full balance, but it already glows with light produced when gravitational energy turns into heat and then escapes from the surface. Infall from the envelope continues and gas spirals through the disk toward the center, so the mass of the protostar climbs steadily with time. Magnetic fields that thread the gas help move angular momentum outward, allowing more material to fall inward instead of remaining in orbit. At the same time, twin flows of gas can emerge along the rotation axis as narrow outflows or jets, carrying away angular momentum and energy and punching holes through the surrounding cloud. These features are seen in many young stars, and similar processes are thought to act during the birth of the most massive stars, even though exact details of the flows and fields remain an active area of research. Deep within, the protostar pressure and temperature slowly rise as more mass accumulates. The gas in the core becomes ionized and radiation finds it harder to escape, so energy moves outward by scattering and absorption rather than by free streaming. The star approaches a state in which the inward pull of gravity is balanced by the outward push of pressure, a condition called hydrostatic equilibrium. For a forming massive star, the approach to this balance is complicated by the continuing arrival of fresh material and by the strong radiation already emerging from its hot surface, but the trend is clear. With growing mass, the central temperature climbs toward the point at which hydrogen nuclei can begin to fuse into helium in a sustained way. Around the forming star, the environment responds to its rising luminosity. High-energy light from the hot surface starts to ionize the nearby gas, producing compact regions of glowing hydrogen. These small ionized bubbles are confined at first by the dense material around them, but as time passes they expand, creating bright pockets inside the surrounding cloud. The outflows and early stellar winds clear some of the closest gas and dust, opening low-density channels through which radiation can escape more easily. Observations of young star-forming regions in the Milky Way show just such patterns, knots of bright emission-slender jets and cavities carved into the darker cloud by the action of newly formed stars. In the most massive clumps, many cores collapse in the same broad region. A cluster takes shape as several protostars, some destined to be massive, share the same supply of gas. Their disks' outflows and radiation fields interact, adding complexity to the pattern of growth. Some objects may gather more material because they sit at favorable positions where filaments converge, while others may lose access to gas as nearby stars heat and disperse the surrounding medium. Gravitational encounters can alter orbits, and in some cases move forming stars away from the densest regions. High-resolution radio and infrared observations reveal these crowded birth environments with bright young massive stars emerging from behind the dust, while other forming objects remain deeply embedded and visible only at longer wavelengths. The timescale for the birth of a massive star is short compared with the timescale for less massive stars. A star like the Sun may spend millions of years contracting toward the main sequence, while a very massive star can reach stable nuclear burning more quickly because of its high accretion rate and intense internal heating. During much of this brief formation phase, the growing star already shines strongly. Its light exerts pressure on dust grains mixed with the gas, and raises the question of how accretion can continue. Modern models indicate that the presence of disks and outflows allows radiation to escape along some directions, while gas feeds the star along others, so the flow of matter does not need to be perfectly symmetric. In this picture, a massive protostar continues to gain mass, even while its radiation sculpts the surrounding cloud. As the envelope thins, the nearby material becomes more transparent. The residual disk close to the star may break up or disperse under the combined action of radiation winds and interactions with companions. The young massive star emerges clearly a very luminous hot object that floods its neighborhood with ultraviolet light. It lights up what remains of the birth cloud as a glowing nebula and pushes other gas and dust outward into the wider interstellar medium. The original dense clump that collapsed has now turned part of its mass into a single, massive star, and possibly several lower mass companions, while the remaining gas drifts away or becomes part of later generations of stars. With this birth phase complete, the massive star stands on the main sequence, ready to begin the period of steady hydrogen burning in its core that defines the next stage of its life in the galaxy. Once the massive star settles into stable nuclear burning, it enters a phase astronomers call the main sequence, during which its structure becomes relatively steady over long stretches of time. In this stage, the central regions of the star quietly fuse hydrogen into helium, releasing energy that moves outward and keeps the star shining. The inward pull of gravity is balanced by the outward push of pressure produced by the hot gas and radiation inside. This balance, called hydrostatic equilibrium, holds the star in a nearly constant shape with a radius and luminosity that change only slowly. For a star with many times the mass of the Sun, this main sequence phase is both intense and brief. It radiates far more energy than a star like the Sun, yet its reservoir of fuel, though larger, is consumed more quickly because the rate of nuclear reactions is so high. The massive star appears as a bright blue or blue-white point of light dominating the region around it with its radiance. Inside the core is extremely hot and dense. Hydrogen nuclei, which are protons, move at high speeds and collide, often overcoming their mutual electric repulsion and merging through a series of nuclear reactions. These fusion reactions produce helium nuclei and release energy in the form of high-energy photons and other particles. The energy generated in the core must then move outward through the star. In some regions, photons scatter many times off electrons and ions, taking a very long time to work their way to the surface. In other regions, rising hot gas carries energy upward, while cooler gas sinks, setting up convective motions. The exact pattern of energy transport depends on the mass of the star, its composition, and its internal structure, but the overall effect is a steady outward flow of energy that supports the outer layers and maintains the star's luminosity. The envelope of the star extends outward from the core through layers where temperature and density gradually fall. At the surface, the gas becomes transparent enough for photons to escape freely into space. The temperature of this surface, called the photosphere, determines the color of the star and the spectrum of radiation it emits. Massive stars have very hot photospheres, with temperatures many times higher than that of the Sun, so they emit strong ultraviolet light in addition to visible light. This radiation bathes the surrounding space and ionizes nearby gas, often producing bright emission nebulae in the star-forming regions where such stars are found. The outer layers of massive stars do not remain entirely still. Strong radiation drives stellar winds, which are flows of gas escaping from the star at high speeds. These winds carry away mass and angular momentum over time. In the densest winds, the mass loss can significantly alter the outer structure of the star, peeling away some of the layers that surround the core. For very massive stars, the blend of radiation, pressure, wind, and rotation can lead to complex shapes and flows in the atmosphere. However, from the standpoint of the core, the main sequence phase remains one of steady hydrogen fusion, with the energy output balanced against the weight of the overlying layers. In many cases, massive stars rotate quickly. This rotation can affect their internal structure, causing mixing between layers that would otherwise be more sharply separated. Rotational mixing can bring fresh hydrogen from outer regions into the core and can move helium and heavier elements outward. The degree of mixing depends on the rotation rate, internal magnetic fields, and other processes that transport angular momentum. Observations of surface abundances and rotational velocities, along with models of stellar evolution, suggest that rotation can extend the main sequence lifetime of a massive star by supplying its core with additional fuel. Even with such effects, the lifetime of a massive star on the main sequence is short compared with that of a star like the Sun, measured in only a few million to perhaps some tens of millions of years. In star clusters, the main sequence behavior of massive stars shapes the appearance of the entire group. Young clusters that still contain the most massive stars appear bright and blue, with these hot objects dominating the light. As time passes and the most massive stars leave the main sequence, the cluster's integrated light becomes redder and less luminous in the ultraviolet. By comparing the properties of stars in a cluster with theoretical models of stellar evolution, astronomers can estimate the cluster's age. The presence of very massive main sequence stars indicates a young population, while their absence and the presence of less massive main sequence stars point to an older one. Thus, the main sequence stage of massive stars not only marks a key phase in their internal evolution, but also serves as an indicator of the history of star formation in their environment. Over the course of the main sequence phase, the chemical makeup of the core changes gradually. Hydrogen is steadily converted into helium, so the fraction of helium in the central region rises. Helium has a different effect on the properties of the gas than hydrogen does, altering the balance between pressure and gravity. To maintain equilibrium and continue producing the same total energy output, the core adjusts its temperature and density. Typically, it slowly grows hotter and denser, while the region where nuclear reactions occur may expand or contract depending on the detailed physics of the star. These internal adjustments proceed smoothly and do not disturb the outer layers, which respond by making small changes in radius and luminosity over millions of years. The star's path in a diagram that relates brightness to surface temperature, often called a Hertzsprung-Russell diagram, is a slowly evolving track along or near the band that defines the main sequence. Around the massive star, the effects of its radiation and winds become clearer as time goes on. Ionized regions in the surrounding gas may expand, forming larger bubbles that push into the cold molecular cloud. Shock fronts can develop where the wind meets denser material, compressing and heating the gas. Some of this compressed gas may cool and fragment, possibly giving rise to later generations of stars at the edges of the cleared cavities. The massive star, now in its long central phase of quiet nuclear burning, thus influences both the form and the future of its neighborhood. Its role is not one of sudden change, but of sustained energy input that gradually reshapes the local interstellar medium. During this time, the star's internal structure remains largely hidden from direct observation. Astronomers infer conditions inside from surface spectra pulsations and comparisons with models that solve the equations of stellar structure. While much of this picture is well established, some details remain under study, such as the exact efficiency of internal, mixing the influence of magnetic fields on rotation and mass loss, and the ways in which small changes in composition affect the lifetime and luminosity of the star. Even so, the broad outline is firm. A massive star on the main sequence quietly converts hydrogen into helium in its core, supports itself against gravity with the pressure of hot gas and radiation, and shines steadily as a brilliant short-lived member of the galaxy's stellar population. As long as enough hydrogen remains in the core to sustain nuclear reactions at the required rate, this steady state continues defining the main sequence phase that occupies most of the star's active life as a stable luminous object. As time passes on the main sequence, the steady conversion of hydrogen into helium in the core gradually changes the internal makeup of the massive star. Hydrogen becomes less abundant in the center while helium accumulates. Helium is heavier per particle than hydrogen, and it responds differently to pressure and temperature. To maintain the same outward flow of energy, the core slowly contracts and heats, adjusting so that nuclear reactions can continue at the rate needed to support the weight of the overlying layers. Eventually, after millions of years of steady burning, the central hydrogen supply falls so low that the star can no longer keep the core in balance using hydrogen fusion alone. The core continues to contract and heat, while hydrogen fusion moves into a shell surrounding the helium-rich center. The star leaves the main sequence and begins a new stage of evolution, in which helium takes over as the main fuel in the core. From the outside, the first clear change is that the star expands. As the core contracts, the energy output from hydrogen fusion in the surrounding shell increases. This additional energy inflates the outer layers, causing the radius of the star to grow. The surface temperature decreases as the photosphere moves outward, and the energy is spread over a larger area, so the star becomes cooler at the surface even as the core grows hotter. Within the star, the helium-rich core reaches temperatures and densities high enough for helium nuclei to begin to fuse. In this process, 3 helium nuclei can combine to form a carbon nucleus, and additional reactions can build oxygen. The onset of helium fusion brings a new source of energy to the core, slowing or halting its contraction. Once again, a kind of balance is reached now with helium as the main fuel. The star spends a period of time in this helium burning phase, though the duration is shorter than the time spent on the hydrogen burning main sequence, because helium fusion releases less energy per unit mass of fuel, and the conditions required are more extreme. The structure of the star now has several distinct zones. At the center, helium fusion produces carbon and oxygen. Around this core lies a shell where hydrogen is still fusing into helium, adding more helium to the core and contributing to the overall luminosity. Above these nuclear burning regions, the extended envelope continues to respond to the energy flowing outward, maintaining the star's enlarged radius and cooler surface. The combination of core and shell burning along with the large radius can drive stronger winds, leading to enhanced mass loss that slowly strips away some of the outer layers over time. As helium burning continues, carbon and oxygen accumulate in the core. When the supply of helium in the core decreases, the balance once again shifts. The core, now composed mainly of carbon and oxygen, contracts further and heats up. In massive stars, the central temperature can rise to the point where carbon nuclei begin to fuse. Carbon fusion produces neon sodium and magnesium among other products, and releases additional energy that supports the core for another shorter phase. Surrounding the carbon-burning core, helium and hydrogen burning proceed in shells, building up more heavy elements toward the center. With each new stage of burning, the pattern repeats. Once carbon is largely consumed in the core, contraction resumes, raising the temperature high enough that neon can fuse, then oxygen and eventually silicon. Each of these phases occurs at higher temperatures and densities than the previous one, and each lasts for a shorter time. Hydrogen burning in the shell may continue for a long period, while helium, carbon, neon, oxygen and silicon burning occur in succession over ever shorter intervals in the most massive stars. Step by step, the core grows richer in heavier elements, and a layered structure develops that resembles an onion in concept, with different nuclear burning processes occurring in shells around the center. In the outer envelope, the star shines as a luminous supergiant. Its surface may show signatures of the processing that has taken place inside, because convection and other mixing processes can dredge up material from deeper layers. Elements such as nitrogen, which are produced in hydrogen burning cycles, can become more abundant at the surface, providing clues about the internal history of the star. Observations of evolved massive stars in the Milky Way and nearby galaxies reveal a variety of spectral types and surface compositions, reflecting differences in mass rotation and mass loss history. Some massive stars become red supergiants with very large radii and cool surfaces. Others evolve into blue or yellow supergiants, or into more compact hot objects with strong winds that strip away their outer hydrogen layers. These different appearances represent variations on the same fundamental process of core burning and shell burning that builds heavier elements over time. While the outer form of the star can vary, the deeper story remains one of successive nuclear stages that convert lighter elements into heavier ones under the influence of gravity and high temperature. Throughout these changes, the environment around the star continues to feel its influence. Intense radiation and stellar winds shape the surrounding gas, while episodes of stronger mass loss inject newly formed elements into the interstellar medium. The material expelled in winds carries carbon, nitrogen, oxygen, and other products of nuclear fusion out into space, where it can mix with the gas that will later form new stars and planets. Massive stars therefore act as important sources of chemical enrichment for the galaxy. Deep inside, the core continues to contract between burning phases, while each new stage of fusion briefly restores balance before the fuel is exhausted. As more heavy elements accumulate, the center of the star becomes denser and hotter, and the pattern of layers grows more complex. Yet at each point along this path, the underlying physics remains the same. Gravity tries to pull matter inward, while pressure from hot gas and radiation pushes outward. As long as some kind of nuclear fusion continues at the required rate in the core or in surrounding shells, the star maintains an overall equilibrium, even though its internal structure and external appearance change significantly over time. In this way, the massive star advances through a sequence of burning stages, gradually building an increasingly heavy core, and a set of surrounding layers that record its past nuclear processes in the arrangement of elements from the center outward. In the late stages of a massive star's life, the layered structure built up by successive burning phases becomes more pronounced and more fragile at the same time. At the very center lies a growing core rich in elements near the iron group, surrounded by shells, where lighter elements are still undergoing fusion. Each shell adds fresh ash to the layers below it, gradually increasing the total mass of the central regions. Gravity remains relentless, pulling all matter inward, while pressure from hot gas radiation and the quantum nature of the electrons in the dense core resists further compression. For a time, this delicate balance holds, but as heavier elements accumulate, the conditions in the center move closer to a point where the usual forms of pressure support can no longer keep gravity in check. The star as a whole still shines as a bright supergiant, but deep inside the core approaches instability in a quiet, unavoidable way. The core that forms in these stages is dominated by nuclei that are very tightly bound with iron, and nearby elements playing a central role. Earlier fusion stages involving carbon, neon, oxygen, and silicon have produced a mixture of these heavy nuclei. Unlike lighter elements, which can release energy by fusing into heavier ones, iron group nuclei do not provide net energy gain when fused further. As a result, once the central composition becomes dominated by these tightly bound nuclei, there is no new source of fusion energy that can turn on in the core to counteract gravity. The core continues to contract slowly, heated by the release of gravitational energy and by residual fusion in surrounding shells, but its ability to find new nuclear fuel in the center is effectively exhausted. Although the temperature and density in the core become extremely high, the usual pathway that would support the star through another stage of burning is no longer available. In this environment, the electrons in the dense core become highly degenerate, meaning that their pressure does not depend primarily on temperature, but on how tightly they are packed. This electron degeneracy pressure, together with thermal pressure and radiation, supports the weight of the overlying layers. However, electron degeneracy pressure can only withstand gravity up to a certain total core mass. As material from shell burning continues to pile onto the core, its mass edges closer to this critical threshold. The core responds by contracting further, which increases its density and temperature, but without the relief that a new energy-generating fusion stage would normally provide. At the same time, energy loss through neutrinos becomes increasingly important. Neutrinos are nearly massless particles that interact only very weakly with matter, so they can escape from the dense core carrying energy away. As temperatures rise, processes that create neutrinos become more efficient, and the core loses energy at a rate that cannot be balanced simply by thermal radiation. This neutrino cooling causes the core to contract more, as it must respond to the loss of internal energy by adjusting to a more compact configuration. Alongside neutrino cooling, other processes contribute to the gradual weakening of the core's pressure support. At very high densities and temperatures, photons become energetic enough to create pairs of electrons and positrons, and these pairs can alter the balance of pressure and particle numbers. As densities rise further, electrons can be captured by protons in nuclei, converting protons into neutrons and releasing neutrinos. This electron capture reduces the number of electrons available to provide degeneracy pressure, and again the core must contract in response. All of these processes are controlled by the local conditions of density, temperature, and composition. The broad picture is that the core loses energy and electron pressure support while gaining mass, driving it slowly toward a state that can no longer remain in stable equilibrium. Around the core, nuclear burning in shells continues for a time. Silicon burning in a shell close to the center can add more ion group material to the core, even as hydrogen and helium burning in more distant shells supply energy that supports the extended envelope of the star. Each burning shell operates on its own timescale, with inner shells evolving more rapidly than outer ones. The innermost stages may proceed on timescales as short as days, while hydrogen burning in outer shells continues over much longer periods. This contrast in timescales means that from the perspective of the outer layers, the star may not show dramatic changes right up until the core crosses its final threshold. The surface still radiates steadily, and the supergiant appearance persists, while the central regions undergo rapid hidden evolution. Theoretical calculations suggest that for cores with masses above a certain limit, close to the mass supported by electron degeneracy pressure alone, no stable configuration exists once the core becomes dominated by ion group elements. Once the core mass crosses this limit, even by a small amount, any further contraction cannot be halted by the available forms of pressure support. In practical terms, this means that the core hovers near a tipping point. Shell burning continues to add mass neutrino cooling, and electron capture continue to drain energy, and electrons and the structure of the core becomes more centrally concentrated. Until that point is reached, however, the star still maintains an overall hydrostatic equilibrium in which the integrated outward pressure balances gravity. The outer envelope remains extended and luminous stellar winds may continue to carry mass away, and the star still shines as part of its cluster or association, even as the core approaches a state in which a new and much more rapid change must occur. In this way, the final approach to instability unfolds quietly within the star. The core grows heavier and denser, supported by electron degeneracy pressure that is gradually weakened by ongoing processes, while ion group nuclei accumulate and remove the possibility of further energy-generating fusion in the center. The surrounding shells keep burning, feeding the core and sustaining the star's brightness, but also pushing the central regions closer to a point where gravity can no longer be balanced. When that point is finally reached, the internal structure of the star is prepared for an abrupt transition, with an iron-rich degenerate core at its heart, and multiple shells of ongoing fusion above it all, enclosed within the vast envelope of a luminous, evolved massive star. As the massive star continues through its final nuclear stages, the iron-rich core at its center approaches the point where no further adjustment can keep gravity balanced. Shells of fusion above the core still convert lighter elements into heavier ones, and deposit fresh material onto the central regions, slowly increasing the core mass. Electron degeneracy pressure and thermal pressure together have held up this inner structure, but each additional layer of ion group nuclei pushes it closer to a critical mass, where this support can no longer suffice. Neutrino losses, electron capture, and other high-energy processes steadily drain energy and reduce the number of electrons available to provide pressure. The core becomes hotter and denser, but without a new kind of fusion to turn on in the center, gravity gains the advantage. When the mass of the iron-rich core finally passes the threshold, that electron degeneracy pressure can support the balance breaks. Inward motion that was once slow becomes a rapid collapse. Regions that had been nearly static in radius begin to fall inward at increasing speed, and the structure that had persisted for thousands of years gives way in a very short time. The timescale of this collapse is much shorter than any of the earlier evolutionary stages of the star, measured in only a fraction of a second rather than in years. Yet it still proceeds in a sequence of well-defined physical steps. At the start of collapse, the inner part of the core moves almost together, with layers remaining in contact as they fall. The density of the gas rises quickly, and electrons are forced into ever smaller volumes. As density and temperature increase, electrons are captured more efficiently by protons inside nuclei, turning protons into neutrons and releasing neutrinos. These neutrinos, which interact only weakly with matter, stream outward and carry energy away from the collapsing core. The electron capture process further reduces the number of electrons available to create degeneracy pressure, deepening the collapse. The matter in the core becomes increasingly neutron-rich, and the pressure that resists gravity shifts from being dominated by electrons to being influenced more strongly by neutrons and by the strong nuclear force that acts between them. As the collapse continues, the inner core approaches densities similar to those inside atomic nuclei. At these densities, the strong nuclear force becomes repulsive at very short ranges, providing an abrupt increase in resistance to further compression. The inner core, which has been falling inward almost freely, suddenly encounters this stiffening of the equation of state, meaning that small further compressions require a great deal of additional pressure. The inward motion of the inner core halts and then reverses, bouncing slightly outward as the matter overshoots the new equilibrium position and responds elastically. This core bounce generates a pressure wave that travels outward through the still infalling outer core. The wave steepens into a shock front as it moves through the rapidly moving layers, marking a boundary between the inner region where matter has been halted and the outer region that is still collapsing. At the moment when the shock forms, the structure of the star is sharply divided. Deep inside lies the extremely dense inner core, supported now largely by nuclear forces and neutron degeneracy. Surrounding it is the outer core, still on its way inward, carrying momentum and mass that must be processed by the emerging shock. Outside the core, shells of fusion and the extended envelope have not yet fully responded to what is happening at the center, because signals cannot travel outward faster than the speed of light, and the collapse develops so rapidly. For a short period, the shock moves outward through the outer core, heating and compressing the infalling matter. Some of the energy of the shock goes into breaking apart heavy nuclei into their constituent protons and neutrons, an energy cost that tends to weaken the shock as it progresses. At the same time, intense neutrino emission continues from the hot dense regions near the center. These neutrinos stream outward, and a small fraction of them deposit energy behind the shock by interacting with matter there. The exact balance among shock heating, nuclear dissociation, neutrino losses, and neutrino heating determines whether the shock can continue to move outward strongly, or stalls for a time. Detailed simulations, which incorporate nuclear physics, radiation transport, and hydrodynamics, indicate that the shock often loses energy initially and can slow or even halt at a certain radius before later being revived by neutrino heating and other effects. The precise sequences and relative importance of these processes are still areas of active research, but the broad outline is clear the collapse of the core, the bounce at nuclear densities and the formation of a shock wave mark the transition from a quasi-static star to a rapidly changing system with a dense central object and infalling outer layers. In the deepest regions, the inner core that has halted its collapse remains at extreme density and temperature. Its exact structure, including the distribution of neutrons, protons, and possibly more exotic particles, depends on the behavior of matter under conditions that cannot yet be fully reproduced in terrestrial laboratories. However, models suggest that the central density exceeds that of ordinary atomic nuclei, and that the matter is arranged in a compact configuration where neutrons play a dominant role. As the collapse phase ends, this dense inner object holds most of the original core mass in a radius of only a few tens of kilometers, while the outer layers of the star are still being processed by the shock and by intense streams of neutrinos. The brief but decisive episode of core collapse has thus transformed the inner regions from a slowly evolving iron-rich core into an extremely dense central body surrounded by shocked infalling material. What happens next to the overlying shells and envelope, and how the star responds on larger scales, depends on how the shock and neutrinos interact with the outer layers. That subsequent evolution unfolds as the collapse-driven changes at the center propagate outward through the rest of the star. When the inner core of the massive star halts its collapse and bounces, the sudden change sends a pressure wave outward into the infalling outer core. This wave steepens into a shock front that moves through matter still rushing inward, converting ordered infall into heated, compressed gas. As the shock advances, it encounters heavy nuclei and breaks them apart into free protons and neutrons, a process that consumes energy and weakens the shock. At the same time, neutrinos stream outward in enormous numbers from the hot, dense regions near the center. Most of these elusive particles pass straight through the surrounding material, but a small fraction interact with matter behind the shock-depositing energy. The interplay between shock propagation, nuclear dissociation, neutrino cooling, and neutrino heating decides whether the shock can overcome the weight of the overlying layers and move outward through the star or stalls and must be revived. In many models, the shock initially slows and may even come close to halting at a radius not far from the center, while matter continues to fall inward from above. Neutrino heating in the region just behind the stalled shock can create buoyant plumes of hot gas that rise outward, while cooler material sinks inward, setting up convective motions in the layer surrounding the newly formed compact core. These motions, along with additional physical processes such as fluid instabilities and perhaps the influence of rotation and magnetic fields, help transfer energy from the neutrino-heated region into the shock. Eventually, under conditions that depend on the mass and structure of the progenitor star, the shock can acquire enough energy to begin moving outward again in a more decisive way. Once the shock is revived, it accelerates through the outer core and into the extended envelope of the star. As it travels outward, it compresses and heats the material ahead of it, then leaves behind gas that is expanding away from the center. The passage of the shock alters the composition of the material it traverses both by breaking apart nuclei and by providing conditions for further nuclear reactions that synthesize new elements. The shock also accelerates the outer layers to speeds that allow them to escape the star's gravitational pull. What had been a hydrostatic envelope supported by internal pressure becomes an expanding shell of gas moving outward into interstellar space. The transition from an intact star to an expanding cloud of ejecta happens over a relatively short time compared with the long prior evolution, though the outermost layers may take hours to fully respond. Seen from outside, the star's surface eventually brightens as energy from the shock and from radioactive decay in the ejected material reaches the outer layers and becomes visible light. The result is a supernova, a luminous event in which the star's brightness increases by many orders of magnitude for a brief period. In a galaxy like the Milky Way, such explosions are rare on human timescales, but when they occur, they can rival or outshine the combined light of billions of ordinary stars for days or weeks. The precise pattern of brightening and fading depends on how much mass is lost, how energy is deposited into the ejector, and how radioactive isotopes produced in the explosion decay and release energy. As the expanding gas travels farther from the center, it cools and becomes transparent. Over years to millennia, the ejecta form a growing shell that interacts with the surrounding interstellar medium. Where the fast-moving gas meets ambient material shocks, develop that heat both the ejecta and the swept-up gas, producing emission in many wavelengths from radio waves to X-rays. The resulting structure, called a supernova remnant, can persist for a very long time as a glowing record of the explosion, with filaments and shells that trace the pattern of expansion and interaction. Observations of such remnants reveal details of the explosion dynamics and the distribution of elements that were synthesized or dispersed during the supernova. The ejecta carry freshly made heavy elements such as oxygen, silicon, and iron into the galaxy, enriching the interstellar gas from which future generations of stars and planets will form. At the center of this expanding scene, the fate of the collapsed core depends primarily on its mass and on the exact conditions achieved during the collapse. If the core mass remains within a certain range, the collapse halts at densities where neutron degeneracy pressure and nuclear forces can support the remnant against further contraction. In that case, the result is a neutron star, a compact object with a mass comparable to that of the Sun, compressed into a sphere only a few tens of kilometers across. If the core is more massive, continued collapse may proceed past the neutron star stage into the formation of a black hole, where matter falls within a region from which light cannot escape. Both outcomes are possible in nature, but for the purposes of tracing the path that leads to neutron stars, the focus rests on those explosions in which a compact neutron-rich remnant survives at the center. The newborn neutron star forms in a very hot and dynamic environment. Immediately after core bounce, it exists as a protoneutron star, still leaky to neutrinos and still adjusting its structure as it cools and contracts. Neutrino emission remains intense, carrying away a large fraction of the gravitational binding energy released in the collapse over timescales of seconds to tens of seconds. As the remnant cools, its outer layers settle, and its radius shrinks modestly toward a more compact configuration. During this early phase, the neutron star may also receive a small net push or kick from any asymmetries in the explosion or in the pattern of neutrino emission. Such kicks can impart a substantial space velocity to the remnant, sending it on a trajectory that may eventually separate it from the center of the expanding shell. Observations of neutron stars displaced from the centers of supernova remnants support the idea that asymmetric processes in the explosion can give the compact object a significant motion through space. The rotation and magnetic field of the neutron star also emerge from this formation process. The core of the massive star likely rotates before collapse, and conservation of angular momentum during contraction causes the newborn neutron star to spin much more rapidly than the progenitor core. Similarly, magnetic fields present in the core can be amplified during collapse, and by dynamo processes operating in the hot convective interior of the protoneutron star. The resulting object may rotate many times per second, and possess a magnetic field far stronger than that of ordinary stars. The full range of rotation rates and field strength depends on details of the progenitor and the explosion, and remains an area of active study, but the general expectation is that the compact remnant is both rapidly spinning and strongly magnetized at birth. While these properties will later shape how the neutron star interacts with its surroundings, and how it appears to distant observers in the immediate aftermath of the explosion, they coexist with the broader transformation of the star into an expanding remnant. In neighboring galaxies and on rare occasions within or near the Milky Way, astronomers have observed supernovae whose properties match those expected from core collapse events. In one well-studied case in a nearby satellite galaxy, detectors on Earth recorded a burst of neutrinos arriving hours before the optical brightening reached its peak, consistent with the picture in which neutrinos escape promptly from the collapsing core, while light takes longer to emerge from the envelope. This kind of observation provides direct support for the theoretical sequence core collapse, neutrino emission shock revival, ejection of the outer layers, and the formation of a compact remnant at the center. Over longer timescales, telescopes reveal expanding shells, knots of heavy elements, and sometimes compact objects embedded within the remnants, all of which together build a coherent view of how the death of a massive star gives rise to a neutron star surrounded by the debris of the explosion. In the end, what was once a stable layered star sustained by nuclear fusion becomes a system composed of two main parts: a rapidly expanding shell of gas carrying heavy elements into the galaxy, and a dense central remnant in which matter has been compressed to densities far beyond those found in ordinary stars. The transformation from one state to the other occurs over a short interval compared with the star's prior lifetime, yet it follows from the same underlying competition between gravity and pressure that has shaped the star at every stage. With the explosion now underway and the envelope streaming outward, the compact core has taken on a new identity as a neutron star, an enduring object that will continue to evolve and interact with its surroundings long after the fading glows of the supernova have dimmed. When the shock from the core collapse has passed through the outer layers of the star and the debris of the supernova begins to drift outward, the newly formed neutron star remains near the center as a compact enduring object. It sits inside a growing cavity in the ejector, still cooling rapidly, but already fixed in its global properties. Its mass is comparable to that of the Sun, perhaps around 1 to about 2 times the Sun's mass, yet all of this matter is confined within a sphere only some tens of kilometers across. This combination of large mass and very small radius gives the neutron star an internal density far beyond that of familiar solids, and a surface gravity so strong that it determines everything that happens close to the star. From this point onward, the neutron star follows an evolution that is quiet when compared with the explosive birth it has just undergone, yet its basic characteristics remain among the most extreme found anywhere in the Milky Way. The gravitational field around the neutron star is intense. An object resting on its surface would feel a pull many billions of times stronger than the gravity at the surface of Earth. The escape speed from that surface, which is the minimum speed a particle must have to move away and not fall back, is a large fraction of the speed of light. Light itself is affected by this gravity, so photons that leave regions close to the neutron star lose some of their energy as they climb outward and arrive at distant observers with longer wavelengths, an effect called gravitational redshift. Space and time in the immediate neighborhood are curved in ways described by general relativity, and orbital paths near the star differ from those around ordinary stars. A small body that passes nearby can be strongly deflected, or can become bound into a tight orbit, while material that ventures too close cannot remain in orbit at all, and must fall inward toward the surface. Despite these conditions, the neutron star behaves as a stable self-gravitating body. inside pressure arising from the properties of dense neutrons and from the strong nuclear force between them balances gravity through most of the interior. Near the outer edge, matter changes rapidly from this dense interior to much lower density material in a narrow transition region that leads out into space. The star as a whole spins as a nearly rigid body carrying its interior and outer layers around a common axis. The exact rotation rate depends on how fast the progenitor core was turning and on details of the collapse, but in many cases the newborn remnant completes a turn in a fraction of a second to at most a few seconds. Over long periods, this spin gradually slows as the star loses energy to radiation and to particles that stream away, yet immediately after formation, it almost always exists as a very rapidly rotating object. The neutron star does not necessarily remain fixed at the geometric center of its supernova remnant. Asymmetries in the explosion and in the emission of neutrinos during collapse can give the compact object a net kick so that it leaves the birth site with a substantial space velocity. Observations of young neutron stars often show them offset from the apparent centers of their surrounding remnants, and measurements of their motion across the sky indicate speeds of many hundreds of kilometers per second in some cases. As the remnant expands and its inner gas becomes more tenuous, the neutron star moves through the interior of the shell and then into the broader interstellar medium. There it continues its motion as a fast-moving compact body orbiting within the Milky Way, following a path set by the combination of this initial kick and the overall gravitational field of the galaxy. For thousands of years it may still lie inside a hot shocked bubble of gas created by the explosion, but as the remnant disperses, this environment becomes quieter and more like the diffuse gas and magnetic field that fill the galaxy. In its youth, thermal radiation from the hot surface can make the neutron star shine strongly in X-rays, because its outer layers are extremely hot immediately after formation. As it radiates away energy, the surface temperature falls and the spectrum of emission shifts toward longer wavelengths. Over millions of years this cooling continues, and the neutron star becomes progressively less luminous, though deep inside it still holds a large reservoir of thermal energy. The cooling history depends on how efficiently neutrinos and photons remove energy from the interior and on the composition and structure of the outer layers that blanket the dense core. Within the broader family of compact objects, neutron stars occupy a middle ground between white dwarfs and black holes. White dwarfs have masses similar to the Sun but radii closer to that of Earth, and they are supported mainly by electron degeneracy pressure. Black holes, by contrast, form when gravity overwhelms all forms of internal pressure and matter collapses within a region from which light cannot escape. Neutron stars represent the outcome for core masses in a particular range where neutron degeneracy and nuclear forces can still halt the collapse before a black hole forms. From the perspective of the galaxy, neutron stars form a population of faint compact points scattered through the disk and the surrounding halo. Their birth rate follows the formation rate of massive stars, so they are more common in regions where star formation has been active in the recent past, such as spiral arms and dense star-forming complexes. Over time, their natal kicks carry them away from their original clusters and associations, populating a wide volume of the Milky Way with compact remnants. The number of neutron stars in the galaxy is thought to be very large, although only a small fraction are detectable with present instruments. Each individual neutron star carries the record of a single massive star's life and death, encoded in its mass rotation magnetic field and motion through space. Even as it cools and ages, the star retains the same basic global properties that make it an extreme object. Its size remains comparable to that of a city, while its mass remains comparable to that of the Sun, its internal density stays near or above nuclear densities, and its surface gravity continues to be so strong that even modest disturbances can release large amounts of energy. The neutron star that remains after the supernova is defined not only by its mass and radius, but also by the extreme conditions at its surface. Surface gravity is so strong that material near the outer boundary feels a pull billions of times stronger than gravity on Earth. An object dropped from a small height above the surface would almost instantly reach a speed close to that of light if it were not destroyed and absorbed. This gravity compresses the outermost region into a very thin transition between the dense interior and the vacuum of space, so the part that can be called an atmosphere is only a small distance thick. Within this narrow layer, density and temperature change rapidly, and photons that have diffused outward from deeper regions scatter their last times before escaping. The behavior of light in this layer determines how the neutron star appears to distant observers and carries information about the conditions at the surface. Although geometrically thin, the atmosphere is very dense compared with familiar gases. Its composition depends on temperature, magnetic field strength, and how much material the star has accreted. In an isolated neutron star that has not recently gathered new matter, heavy elements can sink under gravity, leaving a surface dominated by light elements such as hydrogen or helium. In a system where accretion continues, fresh material can maintain a different mix of elements near the top. In all cases, the strong gravitational field produces a sharp stratification, with high densities at the base and much lower densities higher up. Soon after formation, the surface temperature can reach many millions of degrees Celsius, so the neutron star shines mainly in X-rays. As it ages and cools, the temperature falls, and the peak of the emission shifts toward lower energies, although for a long time the surface remains much hotter than that of the Sun. Light leaving the surface carries the imprint of intense gravity. Photons climbing out of the gravitational well lose energy, so their wavelengths become longer by the time they reach a distant detector. Gravity also bends their paths so an observer can see more than just the hemisphere directly facing them. For typical neutron star masses and radii, calculations based on general relativity show that more than half of the surface can be visible at once, because light from regions near the edge is bent toward the observer. This light bending must be included when modelling observed pulse shapes and spectra, especially for rapidly rotating neutron stars whose emission is not uniform across the surface. Because the detailed form of the spectrum depends on the mass radius and atmospheric structure, careful measurements of surface emission provide one of the main ways to constrain how matter behaves at such high density. The strong magnetic field at the surface further alters the physics of the atmosphere. In neutron stars, magnetic fields can exceed those in ordinary stars by many orders of magnitude. Charged particles move along curved field lines, and their motion across the field is restricted, which changes how they absorb and emit radiation. The opacities that describe how photons interact with matter become different in directions parallel and perpendicular to the field. As a result, radiation emerging from the surface can be polarized, and its intensity can vary with direction. In the most strongly magnetized neutron stars, the field is strong enough to modify the structure of atoms and to shift the energies of spectral lines. Interpreting the spectra of such objects therefore requires models that include both strong gravity and strong magnetic fields. The surface of a neutron star is not always uniform in temperature. The star rotates, and its magnetic axis may not be aligned with its spin axis. Heated regions can form near the magnetic poles if charged particles from the magnetosphere return to the surface and deposit energy in limited areas. In accreting systems, gas that flows along magnetic field lines can strike the surface in small spots near the poles, producing hot regions that outshine their surroundings. As the neutron star spins, these hotter areas rotate into and out of view, causing periodic variations in brightness. When the rotation is stable, these modulations appear as regular pulses, allowing astronomers to measure the spin period with high precision and to follow small changes over time. The detailed pulse shapes and how they vary with energy carry information about the size and position of the hot regions, the properties of the atmosphere, and the bending of light near the star. Even when clear pulses are not seen, surface emission remains a key probe of the neutron star's state. The spectrum of thermal radiation can be used to estimate the effective surface temperature. When such measurements are made for neutron stars of different ages, they can be compared with theoretical cooling curves that describe how the interior loses heat through neutrino emission and photon radiation. The outer layers act as a thermal blanket that regulates the flow of heat from the core to space, so the composition and structure of the atmosphere and the underlying surface directly influence how quickly the star cools. By matching observed temperatures to models, scientists try to infer whether neutrons in the interior form a superfluid, whether protons become superconducting, and how these states change the efficiency of neutrino cooling. Although the interior cannot be seen directly, the way the surface cools over time offers indirect clues to the behavior of matter at densities near and above those of atomic nuclei. At the base of the atmosphere, matter changes from a gas in which atoms and ions move freely to a solid lattice, where nuclei occupy fixed positions in a dense crust. This transition occurs over a very short distance, yet it marks the boundary between the radiating outer skin and the rigid interior. The presence of a solid crust means that the neutron star can support elastic stresses. Over time, gradual shifts in the magnetic field or in the rotation rate can build strain in the outer layers. When that strain is released, parts of the crust can fracture or move, depositing heat into the near-surface region and temporarily altering the local temperature. In highly magnetized neutron stars, such events are thought to contribute to bursts or flares of high-energy radiation, although the detailed mechanisms remain topics of active research. From the standpoint of surface emission, the important point is that the atmosphere rests on a stiff foundation whose slow evolution and occasional adjustments can change the way the star radiates into space. Rotation is one of the defining properties of a neutron star once it has settled from its birth in the aftermath of a core collapse supernova. Before the collapse, the core of the massive star already rotates, perhaps slowly compared with a final compact object, but with a definite angular momentum. During the collapse, the radius of the core shrinks from a size comparable to that of a small star down to a size comparable to that of a city. Because angular momentum is conserved, this large decrease in radius brings a corresponding increase in rotation rate. The newborn neutron star emerges spinning rapidly, often completing a turn in far less time than a human heartbeat. This spin is not a surface phenomenon alone. The entire star, from the dense inner regions to the thin outer layers, rotates almost as a rigid body, so that every point at a given latitude turns together. Over time, this rapid rotation gradually slows as the neutron star loses energy to radiation and to particles that escape along its magnetic field lines. The magnetic field of the neutron star is the second key ingredient that shapes its external behavior. The progenitor star already possesses a magnetic field, and the collapse of the core, along with possible internal dynamo processes in the hot convective protoneutron star, can amplify this field to very high strengths. The result is a compact object whose magnetic field at the surface can be many orders of magnitude stronger than that of the Sun. In many cases, the magnetic axis is not aligned with the rotation axis. This misalignment means that as the neutron star spins, the direction of its magnetic pole sweeps around in space. The magnetic field lines emerge from one magnetic pole, thread the space around the star, and return to the opposite pole, forming a structure known as a magnetosphere. Charged particles near the star are trapped by this field and forced to move along its lines, spiraling and streaming outward along some paths while being confined on others. In the magnetosphere, the rotation of the neutron star induces electric fields that can accelerate charged particles to very high energies. These particles move along field lines that extend outward from the magnetic poles. As they travel, they emit radiation across a range of wavelengths, through processes in which their curved motion in the strong magnetic field causes them to lose energy as photons. Because the magnetic axis is tilted relative to the rotation axis, the beams of radiation produced near the poles sweep around like the light from a rotating beacon. If one of these beams crosses the line of sight to Earth, an observer detects a sequence of pulses at regular intervals equal to the star's spin period. Objects that are seen in this way are called pulsars, and they form one of the most important observational classes of neutron stars. The pulse pattern from a single pulsar can be remarkably stable. Each rotation produces a similar burst of radiation, so the pulses follow one another with high regularity. Small variations can occur due to processes in the magnetosphere, or changes in how emission is generated, but over long times, some pulsars rival the stability of the best timekeeping devices built on Earth. By recording the times of arrival of individual pulses and comparing them with a model of steady rotation, astronomers can detect tiny departures from perfect regularity. These departures reveal how the neutron star loses rotational energy, how its interior responds to changes in spin, and how its motion through space affects the arrival of the pulses. Pulse timing has become a powerful tool for studying the neutron star and for tracing the influence of interstellar gas on the traveling radio waves. The loss of rotational energy is a central feature of pulsar evolution. As the neutron star emits electromagnetic radiation and streams of particles, it carries away angular momentum and energy. The rotation rate therefore decreases gradually, a process known as spin down. The rate of spin down depends on the strength of the magnetic field, the rotation rate, and the configuration of the magnetosphere. In many cases, the slowdown is smooth and can be described by models in which magnetic dipole radiation provides the main torque. In other cases, small irregularities occur. Some pulsars show sudden small increases in rotation rate, often called glitches, which are thought to arise from interactions between the solid crust and more fluid inner components. Between such events, however, the overall trend remains a slow, steady increase in the rotation period as energy is radiated away. The way a pulsar appears to observers depends strongly on the geometry of the system and on the properties of its emission. If the magnetic axis is oriented so that its beams never cross Earth's line of sight, the neutron star will not be seen as a pulsar from our vantage point, even though it may still be rotating rapidly and emitting beams in other directions. When the geometry is favorable, different parts of the beam structure may sweep past, producing complex pulse shapes. Some pulsars show one main pulse, each rotation, others show two, and many display additional components within the overall pulse window. Observations at different wavelengths reveal that radio X-ray and gamma-ray pulses can arise from related but distinct emitting regions within the magnetosphere. By comparing pulse shapes and arrival times across the spectrum, astronomers can map these regions and refine models of how charged particles move and radiate in the strong fields near a fast-spinning neutron star. The population of pulsars observed in the Milky Way spans a wide range of spin periods, magnetic field strengths and ages. Young pulsars are often found near the centers of supernova remnants, still embedded in the gas ejected by the explosion that formed them, and they spin rapidly with relatively large spin-down rates. Older pulsars can wander far from their birthplaces, moving through the general interstellar medium. Their spin periods lengthen, and their pulse energies decline as they radiate away rotational energy. Eventually, for very slow rotation and weak fields, conditions in the magnetosphere may no longer support strong particle acceleration, and radio pulses can cease. The neutron star then becomes difficult to detect, even though it remains an extremely dense compact remnant. Taken together, the observed pulsars provide a detailed view of how rotation and magnetism shape the outer behavior of neutron stars, linking the compact object at the center to the beams of radiation that sweep across the galaxy. Among the many neutron stars scattered through the Milky Way, a smaller group stands out because of their exceptionally strong magnetic fields. These objects, called magnetars, share the same basic structure as other neutron stars, with masses similar to that of the Sun, compressed into radii of only a few tens of kilometers, yet their surface magnetic fields are much stronger than those of ordinary pulsars. In a magnetar, the field can exceed that of typical neutron stars by several orders of magnitude, reaching strength so high that they dominate the physics of the outer layers in the surrounding space. This intense magnetism shapes how the star cools, how it radiates, and how it occasionally releases stored energy in brief bright episodes observed in high-energy light. Despite these striking properties, magnetars still fit within the same overall picture of neutron stars formed in core collapse supernovae, differing mainly in how much magnetic energy they retain and how that energy is organized. The origin of such strong magnetic fields lies in the conditions during and shortly after the formation of the neutron star. If the collapsing core of the massive progenitor star rotates rapidly and has a pre-existing magnetic field, the contraction to a much smaller radius can amplify the field through simple concentration of magnetic flux. In addition, motions in the hot, dense interior of the protoneutron star can drive dynamo processes that further strengthen the field, especially if convection and rotation interact efficiently. The outcome is a compact object whose magnetic field at the surface and in the interior is far stronger than that of most neutron stars. While the details of these amplification processes remain under study, the broad idea is that some fraction of newborn neutron stars emerge with fields so high that magnetic energy becomes a major reservoir in the star, comparable to or exceeding the energy stored in rotation. In such objects, the subsequent evolution of the neutron star is governed more by the decay and rearrangement of the magnetic field than by the loss of rotational energy alone. Magnetars are often identified through their distinctive emission in X-rays and gamma rays. Some are seen as persistent X-ray sources whose luminosity cannot be explained simply by cooling of the surface or by rotational energy loss. Instead, the observed radiation appears to be powered by the gradual decay of the strong magnetic field, which heats the crust and outer layers from within. Others reveal themselves through bursts and flares, sudden enhancements in high-energy output that last from a fraction of a second to several minutes. During these events, the inferred luminosities can rise far above the steady level, indicating that magnetic energy is being released in rapid episodes. The repetition of such bursts from the same object, along with their spectral properties and spin behavior, links them to neutron stars with strong fields rather than to accreting systems or other kinds of compact sources. In quieter intervals between bursts, magnetars can appear as slowly rotating X-ray pulsars, whose emission still carries the imprint of their intense magnetism. The magnetic field of a magnetar threads its solid crust and its magnetosphere, storing energy in twisted and stressed configurations. Over time, the field evolves as it diffuses through the dense matter and reconfigures itself to lower energy states. This evolution can build stresses in the crust because the solid outer layers must adjust to changes in the field that is anchored within them. When accumulated stress exceeds the crust's ability to deform, elastically fractures or sudden shifts can occur. These events, sometimes described as starquakes, can release energy both mechanically and electromagnetically. They can also disturb the anchored magnetic field, allowing it to rearrange and reconnect in ways that accelerate particles and generate bursts of high-energy radiation. In this view, many magnetar bursts arise from the interplay between crustal motions and magnetic field evolution, with the dense, rigid outer layers acting as both a reservoir and a trigger for stored magnetic energy. In addition to bursts, some magnetars have produced even more powerful flares, brief events in which a large portion of the magnetic energy in a localized region is released at once. These giant flares are rare, but when they occur, they can be observed across large distances in the galaxy and beyond. The initial spike of high-energy emission may be followed by a slowly fading tail, modulated at the spin period of the neutron star, indicating that the emission region rotates with the star. Even in these cases, the underlying driver is still thought to be the magnetic field and its reconfiguration. The overall picture remains one of a compact star whose outer layers and surroundings are controlled by an evolving, extremely strong magnetic field that can power both steady emission and sudden outbursts without requiring large amounts of accreted matter from outside. The rotation of magnetars differs in some respects from that of many ordinary pulsars. Magnetars tend to spin more slowly on average, with periods of several seconds rather than fractions of a second. Their spin-down rates are often relatively high, implying strong magnetic torques that remove angular momentum efficiently. As the magnetic field decays and rearranges, the spin-down rate can vary, leading to changes in the measured period derivative and to small timing irregularities. Occasional glitches, sudden small increases in rotation rate also occur, and may be linked to the same internal processes that produce glitches in ordinary pulsars, such as interactions between the solid crust and superfluid components in the interior. Because magnetars emit strongly in X-rays, timing measurements often rely on high-energy photon arrival times, rather than on radio pulses, although a few magnetars have also been detected at radio wavelengths. Taken together, the timing and spectral observations show that magnetars occupy a region of parameter space where strong fields and relatively slow rotation combine to produce a distinctive form of neutron star activity. Despite their energetic outbursts, magnetars still fit into the broader neutron star population as objects that gradually evolve toward quieter states. As the magnetic field decays over timescales of thousands to hundreds of thousands of years, the rate of magnetic heating declines and the frequency and intensity of bursts decrease. The star cools and its surface emission becomes fainter, gradually approaching that of other neutron stars of comparable age if the field decays sufficiently. The long-term endpoint is a compact remnant whose magnetic field, while still strong by ordinary standards, no longer dominates its energetics. From the perspective of the galaxy, magnetars represent a transient phase in the life of some neutron stars during which magnetic energy is converted into radiation and particle outflows that can affect the surrounding interstellar medium. Their strong fields can shape the immediate environment, generate waves and particles that propagate outward, and contribute to the overall population of high-energy sources. Observationally, magnetars have been identified both within and outside known supernova remnants, indicating a range of ages. Those near the centers of young remnants appear to be relatively young objects, whose strong fields have not yet decayed significantly. Others more isolated in the galaxy may represent somewhat older stages in which the surrounding remnant has dispersed. In each case, their high energy emission, slow rotation, and large spin-down rates point to the same underlying physical picture. By studying magnetars across this range of environments and ages, astronomers seek to understand how the strongest known magnetic fields in the universe are generated, how they evolve, and how they influence the behavior of matter under extreme conditions. In this way, magnetars extend the role of neutron stars beyond being simply dense remnants of stellar cores. They act as laboratories for magnetic fields, radiation, and solid matter, all operating at limits far beyond those found elsewhere in the galaxy, while still remaining consistent with the quiet, stable presence of a neutron-rich core at their center. Beneath the thin atmosphere of a neutron star lies a region where matter changes from a gas to a solid in a very short vertical distance. This solid outer layer, commonly called the crust, extends inward for about 1 kilometer in depth and provides a rigid foundation for the atmosphere above. In the outermost part of the crust, densities are lower than in the deeper interior, but still far higher than those found in ordinary solids. Atomic nuclei stripped of their electrons arrange themselves in a regular lattice somewhat like ions in a crystal, while a sea of electrons moves freely between them. The strong gravitational field compresses this lattice tightly, and the high pressure forces nuclei into close proximity. The crust as a whole behaves as a solid that can support shear stresses, meaning it can carry distortions and strains without immediately flowing. This gives the neutron star the ability to store elastic energy in its outer layers, a property that plays an important role in its rotational behavior and in some of its irregular outbursts. Deeper into the crust, density continues to rise and conditions change. At a certain depth, the pressure becomes so great that some neutrons begin to leak out of the nuclei. These free neutrons coexist with the remaining nuclei, and the electron sea forming a mixture of particles that behaves differently from an ordinary solid. In this inner crust region, nuclei may become more neutron-rich and adopt shapes that differ from the nearly spherical forms familiar from low-density matter. The interplay of nuclear forces and Coulomb forces in this regime can lead to arrangements in which matter forms rod slabs or other extended structures, a domain sometimes described using analogies with familiar shapes, although the underlying physics is that of nuclear matter seeking configurations of lowest energy under extreme compression. Free neutrons between these structures can form a superfluid, a state in which they flow without internal friction. This combination of rigid nuclear framework and superfluid neutrons gives the inner crust a complex response to stress and rotation that scientists study through models and indirect observations. The existence of a solid crust and superfluid components is inferred from both theoretical work and from phenomena such as pulsar glitches. In these events, the observed rotation rate of a neutron star jumps slightly in a sudden discrete step, then relaxes over time toward a new steady spin-down trend. One explanation involves the interaction between the superfluid in the interior and the solid crust. As the star spins down, gradually vortices in the superfluid that carry its angular momentum can become pinned to the crustal lattice, storing rotational energy in a non-uniform way. When these vortices suddenly unpin and move, angular momentum can be transferred to the crust, causing the observed small increase in spin rate. The details of this process remain under active investigation, and alternative or additional mechanisms may contribute, but the broad picture links the elasticity of the crust and the presence of superfluid neutrons to observable timing irregularities. In this way, the crust and inner layers reveal some of their properties through the precise clockwork of pulsar rotation. Thermal conduction in the crust also plays a major role in how the neutron star cools and responds to heating. When newly formed, the star is hot throughout, and heat must travel from the interior to the surface to be radiated into space. Electrons in the crust carry heat efficiently along the lattice, and the presence of impurities or irregularities in the nuclear arrangement can alter how well they do so. If the crust contains a high fraction of nuclei with a range of charges scattering, can reduce the thermal conductivity and change the temperature profile. Over time, these microscopic properties affect the observable surface temperature because the crust acts as a blanket that either insulates the interior or allows heat to escape more easily depending on its composition and structure. In accreting systems where matter from a companion star piles onto the surface, additional nuclear reactions occur in the crust as fresh material is buried and compressed. These reactions deposit heat at various depths, modifying the thermal structure and influencing how the neutron star cools when accretion stops. Observations of cooling in transient systems after accretion episodes provide constraints on crustal properties by comparing measured temperatures with models of heat transport and nuclear heating. At the base of the crust, where density approaches that of nuclear matter, the distinction between crust and core becomes less clear. Nuclei become so neutron-rich and so closely packed that they begin to merge into a continuous medium. The free neutrons that have permeated the inner crust blend smoothly into the bulk nuclear matter of the outer core. In this transition region, theory suggests that the exotic nuclear shapes of the deepest crust gradually dissolve as the system moves toward a more uniform composition. The exact thickness and structure of this boundary depend on the equation of state, which is a description of how pressure, density, and energy relate for matter at these densities. Different models of nuclear forces and particle interactions predict somewhat different crust thicknesses and transition densities, and these differences in turn influence global properties such as the mass-radius relation for neutron stars and the maximum mass they can support before collapsing into black holes. The outer core lying beneath the crust consists mainly of neutrons with a smaller fraction of protons, electrons, and possibly muons, all in a state of high density and pressure. In many models, neutrons in the core form a superfluid, while protons form a superconductor, leading to quantized vortices and magnetic flux tubes that structure the internal flows and fields. These ordered structures can interact with the crust and with each other, influencing how the star responds to changes in rotation and how it emits neutrinos and heat. However, direct observational evidence for the detailed arrangement of matter in the outer core is limited, and much of what is known comes from combining nuclear physics calculations with constraints derived from global neutron star properties. Measurements of masses, especially for heavy neutron stars, and of radii inferred from X-ray observations help narrow the range of acceptable equations of state, but significant uncertainties remain. Despite these uncertainties, the layered picture of atmosphere, crust, outer core, and deeper interior provides a coherent framework for thinking about the neutron star as a whole. The crust acts as an interface between the observable surface and the dense interior, transmitting heat, supporting magnetic fields and storing elastic and rotational energy. Its composition and structure are shaped by the history of the star, including its birth conditions, any accretion it has experienced, and the slow evolution of its magnetic field. In turn, the crust influences observable properties such as pulse shapes, timing, irregularities, surface temperatures, and the pattern of bursts and flares in highly magnetized objects. By studying these phenomena carefully and comparing them with models that incorporate crust and outer core physics, astronomers and physicists attempt to refine their understanding of matter at densities and pressures far beyond those accessible in terrestrial experiments. The crust thus serves as both a physical and a conceptual bridge between the accessible outer signals of the neutron star and the more hidden behaviors of its inner core. Deep inside the neutron star, beneath the crust and outer core, lies a region where matter reaches the highest densities that the object can support without collapsing further. This central zone, often called the inner core, holds a large fraction of the star's mass within a sphere only a few kilometers across. In this environment, pressure and density exceed those found in the outer core, and the behavior of matter is controlled by the strong nuclear force in a regime that cannot be reproduced in laboratories on Earth. The composition and state of this inner core are not yet known in detail. Instead, scientists construct models based on nuclear physics, astronomical observations, and the requirement that the star remain in hydrostatic equilibrium, and then compare these models with the measured properties of real neutron stars. Out of this work emerges a picture that is partly secure and partly uncertain, with some general features agreed upon, and other aspects still open. In the outer core, matter consists mainly of neutrons with smaller fractions of protons, electrons, and possibly muons, arranged in a nearly uniform fluid. As density increases toward the center, the balance of particles must adjust to maintain charge neutrality and to minimize the total energy. One broad family of models assumes that the inner core remains a fluid of neutrons and protons with leptons, but with changes in how these particles pair and interact. In this view, neutrons form a superfluid, and protons form a superconductor, creating an array of vortices and magnetic flux tubes. At higher densities, the pairing patterns that describe how particles bind into pairs may change, altering how easily the core can emit neutrinos and conduct heat. The overall effect is that the inner core behaves as a quantum fluid, whose properties differ from those of ordinary nuclear matter, yet still consist mainly of the same basic particles. Other models explore the possibility that new kinds of particles or new arrangements of quarks appear at the highest densities. It may become energetically favorable for some strange quarks to appear inside baryons, giving rise to hyperons, or for matter to move toward a state in which quarks are no longer confined within individual nucleons, but move more freely in a deconfined phase. In such scenarios, the inner core could contain hyperon-rich matter, a mixed phase of hadrons and quarks, or even a core of almost pure quark matter. Each of these possibilities changes the equation of state, generally making matter more compressible at a given pressure. This in turn affects how much mass a neutron star of a given radius can support, and what the maximum possible mass is before collapse to a black hole becomes inevitable, because different candidate equations of state predict different mass-radius relations and different maximum masses. Precise measurements of neutron star masses and radii provide indirect tests of what might exist in the inner core. Observationally, several neutron stars have been found with masses around twice that of the Sun. The existence of such heavy neutron stars rules out models in which the equation of state is too soft, meaning that matter yields too easily to compression at high densities. If too much softening occurs due to the appearance of hyperons or deconfined quarks, the maximum mass allowed by the model falls below the observed values, and that version of dense matter must be discarded or modified. In this way, each new precise mass measurement helps narrow the range of acceptable inner core descriptions. Measurements of radii inferred from X-ray observations of thermal emission or from modeling of X-ray bursts provide additional constraints by limiting how compact a neutron star of a given mass can be. Together, mass and radius data carve out a region in the plane of possible properties within which any viable inner core model must fit. The cooling behavior of neutron stars also offers clues. In the dense inner core, neutrino emission processes can vary significantly depending on composition and pairing states. Some reactions can emit neutrinos very efficiently if the required combinations of particles are present, while others proceed more slowly and emit fewer neutrinos. The presence of superfluidity and superconductivity changes how easily particles participate in these reactions, and can either suppress or enhance neutrino emission at certain temperatures. By comparing observed surface temperatures of neutron stars of different ages with theoretical cooling curves calculated for different inner core compositions, scientists look for patterns that favor some models over others, even though uncertainties in the envelope and crust properties complicate the comparison. Even with these constraints, the precise composition of the inner core remains uncertain. It is likely that neutrons, protons, and leptons still play a central role, but whether they coexist with hyperons, meson condensates, or deconfined quark matter is not yet settled. The densities involved, several times those of atomic nuclei, are beyond the reach of current experimental facilities, so theoretical calculations must extrapolate from known nuclear physics into this more extreme regime. Different approaches yield somewhat different predictions when extended to the highest densities, and reconciling these with observations is an ongoing task. In this situation, the inner core of a neutron star stands as a natural laboratory for matter under extreme conditions. Its global properties such as mass radius, maximum supported mass cooling rate, and related quantities can be measured or constrained, and each of these measurements feeds back into the models of dense matter. Observers can access only these global quantities and surface emissions, not the inner core directly. So the picture that emerges is one in which some features, such as the need for a sufficiently stiff equation of state to support heavy stars, are well established, while other features, such as the exact mixture of particles at the highest densities, remain open questions. The inner core therefore appears as the deepest and most uncertain layer of the neutron star, where current knowledge consists of a set of allowed possibilities, constrained by astrophysical data and by the known laws of nuclear and particle physics, but not yet pinned down to a single definitive description. In many regions of the Milky Way, neutron stars do not travel alone but move in partnership with other stars. In such binary systems, two objects orbit a common center of mass and may exchange matter as they evolve. Some binaries survive the supernova that creates the neutron star, while others form later through interactions in dense clusters. Once a compact remnant becomes part of a pair, its behavior is shaped not only by its own gravity, rotation, and magnetic field, but also by the steady pull and possible mass outflow of its companion. Through these interactions, neutron stars reveal aspects of their physics that are not accessible when they are isolated in space. When the companion is a normal star still burning nuclear fuel, the pair can evolve until the companion expands and fills the region of space in which its gravity dominates. Gas near the point where gravity from both objects balances can then flow toward the neutron star. Because this gas carries angular momentum, it does not fall directly inward, but forms an accretion disk, a rotating structure in which material spirals inward. Friction and magnetic turbulence in the disk convert gravitational energy into heat, so the disk glows often strongly in X-rays. Near the neutron star, the inner edge of the disk may be disrupted by the star's magnetic field, which channels the gas along field lines onto small regions near the magnetic poles. There, the material decelerates heats to high temperatures and radiates in X-rays. As the neutron star spins, these hot regions rotate into and out of view, producing regular X-ray pulses that allow observers to measure the spin period and its slow change over time. Accretion does more than generate high-energy light. Gas flowing from the companion also carries angular momentum, so it can gradually spin the neutron star up. Over long intervals, this process can transform a slowly rotating neutron star into a very fast rotator, with a period of only a few thousandths of a second. Such objects, called millisecond pulsars, often show extremely stable pulse trains and small spin-down rates, indicating that much of their rotational evolution has occurred during the accretion phase. Many millisecond pulsars are found with low mass companions in old stellar populations, consistent with the idea that they were spun up in long-lived binaries. Their steady pulses make them useful tools for probing neutron star interiors and for tracing conditions in the interstellar medium along their lines of sight. Accreting neutron stars can also show brief thermonuclear flashes on their surfaces. When matter rich in hydrogen and helium accumulates in a thin layer, pressure and temperature at the base gradually rise. Under some conditions, nuclear burning in this layer becomes unstable, and in a short interval the stored fuel undergoes rapid fusion. The sudden release of energy appears as an X-ray burst that rises and fades over seconds to minutes. The detailed light curve and spectrum of a burst depend on the surface gravity, the rate at which matter is supplied, and the composition of the accreted gas. By comparing observed bursts with models, scientists can infer properties such as the compactness of the neutron star and the way radiation escapes its strong gravitational field. In this way, binary systems where accretion occurs provide a laboratory for studying both surface nuclear processes and the behavior of matter under extreme gravity. Most striking of all are systems where two neutron stars orbit each other. In such pairs, the orbit slowly shrinks because the system emits gravitational waves, ripples in space-time predicted by general relativity. The loss of energy to gravitational waves leads to a gradual inspiral, which can be measured with high precision in some binary pulsars by tracking changes in their orbital periods. The observed orbital decay agrees with predictions for gravitational radiation, providing strong evidence that these waves carry energy away from the system long before the final merger. As the two neutron stars come closer, their mutual tidal forces deform them, and their orbital period decreases to only a few milliseconds. In the final moments before coalescence, the amplitude and frequency of the gravitational waves rise in a characteristic pattern that can be recorded by detectors on Earth. When merger occurs, some of the neutron-rich matter is ejected into space at high speeds. In this ejector, rapid neutron capture reactions, often called the R process, build very heavy nuclei, including elements heavier than iron. The radioactive decay of these new nuclei powers a transient glow known as a kilonova, which can be observed at optical and infrared wavelengths. The color and brightness of the kilonova change over days to weeks as the ejecta expand and cool, and their behavior encodes information about how much material was thrown out and what elements it contains. The object left behind after a neutron star merger may be a more massive neutron star or a black hole, depending on the total mass and on how matter behaves at extreme density during the collision. If the merged mass does not exceed the maximum that neutron star matter can support, the remnant can remain as a compact, rapidly rotating neutron star that gradually sheds rotational energy. If the mass is larger, the remnant may briefly survive as a differentially rotating object before collapsing to become a black hole. The exact path depends on the equation of state that relates pressure and density in the inner core, so gravitational wave observations of mergers combined with electromagnetic measurements of the ejector place constraints on dense matter physics. Tidal distortions during the last orbits imprint signatures on the gravitational wave signal, and these signatures depend on how easily each star can be deformed, which in turn reflects its internal stiffness. Across the Milky Way and in other galaxies, neutron stars in binaries and mergers thus connect small-scale physics to large-scale cosmic change. They act as engines that convert gravitational energy into radiation in accreting systems as precise clocks in pulsar binaries, and as sites where some of the heaviest elements are forged during mergers. Their interactions with companions return processed material to the interstellar medium and send out gravitational waves that carry information about their masses and internal structure. At the same time, the basic picture established for isolated neutron stars still applies: a compact object with a dense interior, a solid crust and a magnetized exterior, now placed in a setting where exchange of mass and angular momentum with a partner shapes its evolution over long spans of time. Even with decades of observation and theoretical work, neutron stars still keep many of their deepest properties partly hidden, leaving a picture that is clear in outline but incomplete in detail. The existence of these compact objects as remnants of massive star collapse is secure, as are their typical sizes, masses and roles, as pulsars, magnetars and members of binary systems. Their layered structure, with a thin atmosphere, solid crust and dense core, is also well supported by both models and observations. Yet questions remain about how matter behaves under the highest densities in the inner core, how superfluid and superconducting components arrange themselves, how magnetic fields are generated and evolve over long times, and how all of these ingredients combine to shape the signals that reach distant detectors. Neutron stars thus stand as both understood and mysterious objects, providing a stable framework for interpretation, while still challenging attempts to describe every layer precisely. A central open question concerns the equation of state of dense matter, the relation between pressure density and internal energy in the conditions found at the greatest depths of a neutron star. Different microscopic models of nuclear forces and particle interactions lead to somewhat different equations of state, which in turn predict different mass-radius relations and maximum masses. Precise mass measurements of heavy neutron stars combined with radius estimates from X-ray observations already rule out some of the softest equations, but a wide range of possibilities remains. The inner core may contain only neutrons, protons and leptons in unusual pairing states, or it may host hyperons, meson condensates or deconfined quark matter. Each option changes how compressible the core is and how readily it emits neutrinos, affecting both the global structure and the cooling history. Observations continue to refine the allowed region, yet the exact composition at the highest densities remains uncertain. Another unresolved area lies in the behavior of superfluid and superconducting components inside the star. Evidence for superfluidity comes from cooling curves and from timing irregularities such as glitches, which suggest that neutrons and protons form paired states, and that vortices and flux tubes structure the interior. However, the exact pairing patterns, the strength of the interactions, and the way vortices and flux tubes move and pin to the crust or to one another are not fully known. These microphysical details influence how angular momentum is transferred between the crust and interior, how the star spins down, and how it responds to stress. Improved models and more precise timing observations may help clarify how the internal quantum fluids behave, but for now many aspects of their dynamics remain inferred rather than directly determined. The origin and evolution of the strongest magnetic fields also raise open questions. It is broadly understood that fields in neutron stars arise from flux conservation during collapse, and from dynamo action in the hot proto-neutron star. Yet the conditions that lead to magnetar-level fields in some objects, but not in others, are still under study. The internal geometry of the magnetic field, including how much energy resides in toroidal and poloidal components, affects both the stability of the configuration and the ways in which magnetic energy can be released. Over long time scales, the field evolves through processes such as ohmic decay Hall drift and ambipolar diffusion, but the relative importance of these mechanisms under different conditions is not fully settled. Observations of magnetars and high-field pulsars give clues about field strengths and decay rates, yet connecting these clues to a complete theory of magnetic evolution inside neutron stars remains a work in progress. Neutron star mergers add further layers of uncertainty, even as they provide new constraints. Gravitational wave observations have begun to measure how easily neutron stars deform under tidal forces near merger information that feeds back into the equation of state. However, interpreting these signals requires modeling of the merger dynamics and of the matter ejected into space. The exact amount of mass lost, the distribution of velocities, and the composition of the ejector depend on the internal structure of the stars and on how they interact during the final orbits. These details influence the brightness and colour evolution of the kilonova that follows, as well as the pattern of heavy elements produced by rapid neutron capture. Combining gravitational wave data with electromagnetic observations offers a way to probe neutron star physics, but the models linking interior structure to observable signals still carry uncertainties that must be reduced through further work. At a broader level, questions remain about the formation channels and population statistics of neutron stars. The distribution of birth masses, spin periods, and magnetic field strengths is not yet mapped with high precision. Some neutron stars are born in supernovae that leave clear remnants, others appear in older stellar populations without obvious associated shells, and still others arise in dense clusters where encounters and exchanges can build complex binary systems. The rate at which different kinds of neutron stars form the fraction that become magnetars or millisecond pulsars, and the typical paths by which these classes evolve from one stage to another are all topics of ongoing research. Surveys at radio X-ray and gamma-ray wavelengths continue to add new members to the neutron star family, filling in parts of the overall population map but leaving gaps that must be addressed with future instruments and analyses. Even with these open questions, the broad physical picture of neutron stars remains stable. They are compact remnants of massive star cores supported against further collapse by the properties of dense nuclear matter and organized into layers that range from a thin atmosphere and solid crust down to a dense inner core. They rotate, carry strong magnetic fields, and interact with their surroundings through radiation particle outflows and gravitational waves. Current uncertainties concern the detailed microphysics of the deepest layers, the exact mechanisms of emission and field evolution, and the statistical patterns that describe their formation and long-term fate. As observations and theories improve, these uncertainties will narrow, but the essential image of neutron stars as extreme yet stable objects in the galaxy endures, providing a consistent backdrop for exploring the subtler aspects of their internal structure and behavior.